In this lecture, we will discuss observables in quantum mechanics. So let's recall that in quantum mechanics, the space of states V. So this is a complex vector space with a Hermitian scalar product. And mathematically, observables. So this is how we can do observations in quantum mechanics. So these are given by self-adjoint or another word for this is Hermitian operators on V. So let's give a definition. An operator A from V to V is called self-adjoint if for all V and W in V, we have the following property, that the scalar product of V with AW is equal to the scalar product of AV with W. So what does this definition tell us for the standard Hermitian product? So suppose we have standard Hermitian product. On Cn, right? So now we take complex n-dimensional vector space, right? And the standard Hermitian product of V with W is given by the formula. So it's V bar transpose, right? So usually we treat vectors from Cn as columns. So here, when we take the transpose, we get the row vector. And this bar means complex conjugation, so times W, right? And so if we write for this scalar product the self-adjoint property, right? So if we write V with AW, so this becomes V bar transpose times A times W. And if we write AV with W, so this becomes AV bar transpose times W. And what is this? So this is, so when we take the transpose of the product, then it's the product of transposes in the opposite order. So this becomes V bar transpose times A bar transpose times W. And so if this equality holds for all W and V, so then this implies that these two matrices must be equal. So that A is equal to A bar transpose, right? So this I leave you as an exercise, right? So show this, and basically I'll give you a hint that take as V the standard basis vector EI, and for W take the standard basis vector EJ, and then this equality is equivalent to saying that Aij is equal to Aji bar, right? So since this holds for all V and W, so we can take V and W like this, and then show that this will give this, which means that A is equal to A bar transpose. Now let's analyze a little bit this relation and see how difficult it is to recognize when an operator is self-adjoint, or how easy it is to create self-adjoint operators. So to analyze this equality, let's write down matrix. So let's separate real part of this matrix from imaginary part. So let's write A as B plus I times C. So now B and C are real matrices. Then so if I write A bar transpose for this, so this becomes B plus IC bar transpose. So when we conjugate B, because it's a real matrix, it doesn't change. So we get B transpose. And when we conjugate this I, it becomes minus I. So it will become minus I C transpose. And for self-adjoint matrices, we must have equality. So this means that this must be equal to B plus IC. So what we see here, so now we can compare real parts and imaginary parts. So what we see is that B transpose must be equal to B, and C transpose must be equal to minus C. So what we see is that a matrix is self-adjoint if its real part is symmetric. So here B transpose is equal to B, so this means that it's a symmetric real part. And its imaginary part is skew symmetric. Now, as an example of such a matrix, so we can get something like this. So 2, 1 plus I, 1 minus I, and 3, right? So this matrix, so it has, so it's a real part of this matrix is 2, 1, 1, 3. So this is symmetric. So if we take the transpose of this matrix, then it doesn't change. And the imaginary part will be, so if we take terms with I and pull I out, so it will be 0, 1, minus 1, 0. Right? And we can see that this matrix is skew symmetric. And recall that a skew symmetric matrix must have zeros on the diagonal. Right? So this means that self-adjoint matrix must have real entries on the diagonal. Let's discuss the properties of self-adjoint operators. So we have the following theorem. So let A be a self-adjoint operator on a Hermitian vector space V. Then A, every eigenvalue of A is real, and B, eigenvectors corresponding to distinct eigenvalues are orthogonal to each other. Let's give the proof of this theorem. So we start with part A. So suppose we have an eigenvector. So V is an eigenvector for A. So this means that A applied to V is equal to lambda V. Now, let's calculate two things. So let's calculate V with AV. So since V is an eigenvector, so this is equal to V with lambda V. And this is a Hermitian scalar product, so we can pull lambda out from the second factor. So this is equal to lambda times VV. Now, because A is a self-adjoint operator, by definition, it's also equal to AV with V. And now, so again, so it's the same V, so it's an eigenvector, so this is equal to lambda V with V. And here, because of sesquilinearity of the Hermitian scalar product, when we pull the constant out of the first factor, it comes out with the conjugate. So it's equal to lambda bar times VV. Well, by definition of an eigenvector, V is not zero. And this implies, by the properties of a Hermitian scalar product, so a Hermitian scalar product is positive definite. So this means that when we take scalar product of a non-zero vector with itself, the result is non-zero. And in fact, it is a positive real number. And then from this equality, right, so here we have lambda VV is equal to lambda bar VV. And the scalar product of V with itself is non-zero, so this implies that lambda is equal to lambda bar. So if a complex number is equal to its conjugate, then this implies that lambda is in fact a real number. Right? So what we see is that if we have an eigenvector for A, then the eigenvalue must be a real number. The proof of part B is rather similar. So suppose now we have two eigenvectors. So AV is equal to lambda V, and AW is equal to mu times W. And what we say is that these eigenvalues are distinct. So this means that we assume that lambda is not equal to mu. So from here, for example, it will mean that, and lambda and mu are real, right? So from part A. So lambda and mu are real numbers. Now, let's calculate V with AW. So that is equal to V with mu W. And this is equal to mu V with W. And let's calculate. So this, by definition of a Hermitian operator, this is also equal to AV with W. And so this is equal to lambda V with W. And because lambda is real, so when we take it out, we just get lambda times VW. And now these two things are equal. So this implies that if we take the difference between the two, so this tells us that lambda minus mu times VW is equal to 0. And so we said that lambda is different from mu. So this implies that the scalar product of V with W is equal to 0. And this means that these two vectors are orthogonal to each other with respect to the Hermitian scalar product. And so this is exactly what we had to prove. So we had to prove that if we have two eigenvectors that correspond to unequal eigenvalues, then these two eigenvectors are orthogonal to each other with respect to the Hermitian scalar product. Now let's look at a quick example. So suppose we have the following matrix. So we have 1, I, minus I, 1. So let's see, what are the eigenvectors for this matrix? Well, they're easy to find. So we have, so V1 is going to be the vector 1I, and V2 is the vector 1 minus I. Right, so if we multiply the first vector by A, so here we're going to get 0 and 0. And if we multiply the second vector by A, then so here we're going to get I times minus I is plus 1. So we're going to get 2 here. And we're going to get minus I plus minus I. So this is going to be minus 2I here. Right? And so what we see is that the eigenvalues are lambda 1 is equal to 0 and lambda 2 is equal to 2. And so this operator here is self-adjoint because its a real part is symmetric and its imaginary part is skew-symmetric. And we see indeed that the eigenvalues are real, right? So the eigenvectors themselves are not real, but the eigenvalues are real numbers. And so for part B, so part B claims that if we have two eigenvectors with distinct eigenvalues, which they are, then the scalar product of V1 with V2, right? So what is this? So this is V1 bar transpose times V2. So let's calculate. So when we take transpose, so this becomes a row vector, and we need to take its complex conjugate. So it becomes 1 and minus I. And we multiply this by V2, which is 1 minus I, the column vector. And so minus I times minus I is minus 1. So we get 1 minus 1. So that's 0. And indeed, so we see that the Hermitian scalar product of these two vectors is equal to 0. So they are indeed orthogonal with respect to our scalar product. And so this is in agreement with this theorem. Now let us state another theorem that gives a much more complete description of self-adjoint operators. So this is called Spectral Theorem. A self-adjoint operator A on a finite dimensional Hermitian space V is diagonalizable. And combining with the previous theorem, we obtain the following result. So there exists an orthogonal or even orthonormal basis of V, say V1 through Vn, of eigenvectors of A with real eigenvalues. So this means that A Vj is equal to lambda j Vj, where lambda j is a real number. And so these eigenvectors are orthogonal to each other. So Vj with Vk is equal to 0 if j is different from k. Right. So what we get is that we can choose an orthonormal basis of V in which the matrix of A becomes a real diagonal matrix. And so even though we stated this theorem in the context of finite dimensional vector spaces, so in fact there is even a generalization of this theorem to infinite dimensional Hermitian vector spaces. And I wanted to point out that in our first theorem we never used the fact that V is finite dimensional. So the first theorem applies to finite dimensional and also infinite dimensional Hermitian spaces. So for the second theorem, we stated for finite dimensional spaces because we only will need in this course this theorem for finite dimensional vector spaces. But there is a generalization of this theorem for infinite dimensional vector spaces as well. We are not going to prove the spectral theorem, so this theorem is proved in the course of linear algebra, and so we're going to assume it as it stands. And I just wanted to mention here that so if we look for self-adjoint matrices that are real, right? So if a matrix has no imaginary part, then a real self-adjoint matrix is just a symmetric real matrix. And so the spectral theorem applies to real symmetric matrices as well. So if we are not interested in a complex setting, then so this theorem says that for a real symmetric matrix, there is an orthonormal basis in which this matrix is diagonalizable and all eigenvalues are real. An interesting thing is that if you want to prove this theorem just for real matrices, you still have to go to complex numbers and you have to consider this wider class of self-adjoint operators. So in order to prove this theorem for real symmetric matrices, you need to state the spectral theorem in the way how we stated here. So deal with Hermitian spaces and not just dot products with Rn. The notations that we use in quantum computing come from quantum mechanics and they were developed by the physicists. And in particular, physicists use this Bra-Ket notations. So when we write a Hermitian product on Cn, right? So if we take V to be Cn, then so this Hermitian scalar product is equal to V bar transpose times W. So what physicists do is they decouple things in this notation. And so they would write separately this, and they will write separately this. Right? And so this is called, so this one is called the Bra vector, and this is called the Ket vector. And together they form a Bra-Ket. And so basically, mathematically, so this one is just the usual column vector in Cn. Right? So our convention that we write vectors as columns. And then, so what's a Bra? So the Bra is the same as V bar transpose. So this means that this is, now this becomes a row vector. And so then, so for self-adjoint operators, so we have the property that V with AW is the same as AV with W, right? Or in terms of the standard product on Cn, so this means that V bar transpose times A times W is equal to, well, AV bar transpose times W, which is equal to V bar transpose times A bar transpose times W. And so to emphasize the fact that this A can go from left to right, so physicists sometimes write this in the following way. So it's V, then bar A, bar W. So, and this means the following, that so you have an operator which you can apply either to W, right? So this is the standard action of operator on a column vector, right? Or you can apply this operator to the left factor, to a Bra, right? And so then, so what you have is that V and then A acting on a row vector. So this is equal to V bar transpose times A bar transpose. So this is how we can define the action of self-adjoint operators on Bra vectors. And so then we apply A either to the right factor or to the left factor, and then take the scalar product. So, but because the operator is self-adjoint, so it doesn't matter whether we want to apply it to left factor or to right factor. And this notation invented by physicists emphasizes this duality, that this operator A can be applied to either factor here. Now, let us discuss measurements in quantum mechanics. How do we measure properties of quantum mechanical systems? And so how do we run physical experiments? Now, let us look at polarization of a photon. So how can we measure polarization of a photon? So imagine that we have a photon that flies on this trajectory. And so here on its path, we put a filter, so which is called polarization filter. Right, so polarization filter. And with say vertical polarization. So what happens is that vertically polarized photons will pass, and horizontally polarized photons will get reflected. So this means that if this photon has vertical polarization, then it will pass through this filter and will just continue on the same trajectory. And if this photon has horizontal polarization, then it will get reflected and will just fly back, right? So it will either pass through the filter or will get reflected. But, so last time we discussed polarization states of a photon, and we saw that the states are not necessarily vertical or horizontal. So we could also have non-basic states. So suppose so our photon is polarized at an angle. So suppose the state is, so if it's polarized at an angle alpha here, right? So then, so it will be sine alpha times the vertical state plus cos alpha times horizontal state, right? So suppose we have a photon in this state. And so what happens now if this photon comes to this vertically polarized filter? So it turns out that the outcome of this interaction between the photon and the filter is probabilistic. So we get probabilistic outcome. And what will happen is there are two possible outcomes. So with probability sine squared alpha, it will pass. And after it passes through the filter, it will acquire vertical polarization. And with probability cos squared alpha, so which is the square of, or the square of the norm of this coefficient, it will get reflected. And become horizontally polarized. So whatever passes through this polarization filter will be strictly vertically polarized, and whatever gets reflected will be horizontally polarized. So what we see here is that in this, so the measurement process has two important features. One feature, that it is probabilistic. So with a single photon, we cannot predict the outcome of the measurements. So the outcome is probabilistic, and the probabilities are determined by the state of the photon. And so the second feature is that any measurement will change the state of our quantum system. So this means that when we perform a measurement on a quantum system, this is a violent act. So we cannot perform the measurement without changing the state of the quantum system. These two features of the measurement process create huge challenges for quantum computing. A, we don't know exactly what to expect. So the outcome of a measurement is probabilistic. And B, so this measurement process changes the quantum state. And so this means that we can only use measurements very sparingly. And so typically with quantum computing, so you run your quantum algorithm and then you perform measurements once at the very end of your procedure. In a lab setting, it's rather difficult to get one individual photon. So it is possible, but it's a tricky thing to do. So it's much easier to generate a beam of photons in an identical polarization state. And so then, for each photon, the outcome is probabilistic, but then we get laws of large numbers. And so this means that this portion of the beam will pass, and this portion of the beam will get reflected. So what we see here is that we create a beam splitter, and so we see the beam intensities on the output, right? And of course, note that the sum of these two probabilities must be equal to 1. And if you get glasses from a movie theater, you can run nice experiments at home. And so by turning one filter relative to another, so you will see how these lights will get darker or lighter. And so this is basically, you can see the sine squared and cos squared just right in your own hands. Now let us discuss how can we measure spin of an electron. So here we again imagine that we have a beam of electrons. And so we want to measure their spin, right? So how can we do the measurements? So what we can do is, so we can pass this beam of electrons through a strong magnetic field. And so suppose this magnetic field is vertical. And so we have a strong magnetic field. Then what will happen is that this beam of electrons will split into two beams, right? So these here we will have spin up, and the second beam will consist of electron with spin down. And again, so if your electron that flies here has vertical spin, then, or the spin that is up, then it will fly on the trajectory that corresponds to this spin up beam trajectory. If this electron has a down spin, then it will fly on a trajectory that corresponds to down spin. But if the state of your electron is mixed, right? So it's not a basis state. So if we have the following, so if we have A times so spin up, right? So this is up, corresponds to the direction of the magnetic field that we impose here. So here we assume that we have a vertical magnetic field, plus B times spin down. Right? So this is how we wrote last time states, spin states of an electron. Then, so with probability norm of A squared, we will observe spin up, and so the new state will be the basic state spin up, right? And with probability norm of B squared, so we will observe spin down, so meaning that this electron will fly on the second trajectory, and so new state will be the basic state spin down in z direction. Now, let us state the general axiomatics of measurements in quantum mechanics. So, to each measurement experiment, we can associate an observable. So this is a self-adjoint operator A on the space of quantum states of these quantum mechanical systems V. By spectral theorem, so A has a basis, an orthogonal basis of eigenvectors, or generally we can have this eigenspace decomposition. So A has an eigenspace decomposition. So this means that the whole space V decomposes as a sum of eigenspaces. So V lambda 1 plus V lambda 2 plus V lambda k, where so lambda j's are distinct real eigenvalues of A. So suppose our quantum system is in state V, which is a vector in this space of states, and we apply a measurement to this quantum system that corresponds to this observable A. So what will be the outcome? So what we need to do is we need to decompose this vector according to this eigenstate decomposition. So decompose V as V1 plus Vk, where each component is an eigenvector. So Vj belongs to V lambda j. So this means that Avj is equal to lambda j Vj. So when we perform this measurement, the outcome is probabilistic. So with probability which is equal to norm of Vj squared, we observe value lambda j, and the quantum system collapses to state Vj. So this means the following, that, okay, so here we have a decomposition of a vector into these eigen spaces, right? And so we recall that our state, initial state, is normalized, right? So we assume that norm of V is equal to 1, right? So this is one of our postulates in quantum mechanics, that the physical states are states with norm 1. And so here we have that these subspaces are all orthogonal to each other. So the generalization of Pythagoras theorem will say that norm of V in this situation is equal to norm of V1 squared plus norm of Vk squared, right? And so this is equal to 1. So this means that we can interpret these norms of components as probabilities. And so what we say here is two things. So the outcome of a measurement is probabilistic. We can only predict probabilities of observing different outcomes. And secondly, that after we perform the measurement, the original state is destroyed. And so the new state is always a basic state. So it's going to be necessarily an eigenstate that corresponds to the eigenvalue that we have observed. Now, as an example, so let's consider again the spin of an electron. And suppose we have psi is A times spin up plus B times spin down. Right, so where A and B are complex numbers. And so norm of psi is equal to 1, or squared is equal to 1. So this means that norm of A squared plus norm of B squared is equal to 1. Now, what is the observable here? So the observable is 1/2 of 1, 0, 0, minus 1. Right? And this 1/2 is because physicists like to say that spin of an electron is plus 1/2 or minus 1/2. And so what we see here is that eigenvectors here are the basis vectors, right? So E1, which is the spin up vector, right? And E2, which is spin down vector. And so the eigenvalues, so the first eigenvalue, well, this matrix is already diagonal, so here is 1/2. And the second eigenvalue is equal to -1/2. So according to our axiomatics, so if we have this state, then with probability norm of A squared, so with probability norm of A squared, we observe +1/2, and the new state will be a basic state, which is this, right? And so with probability norm of B squared, so we observe -1/2. And so new state will be spin down here, right? Okay, so maybe I should say that so when the system collapses to this pure state, then it needs to be renormalized. So this means that the new state is not really Vj, but Vj divided by norm of Vj. So this is a correction that we need to make here. Now, for quantum computing, we really only need one observable. So recall that a state of, say, we have n qubit. So then this state can be written as the sum k goes from 0 to 2 to the n minus 1 ak times the state k. And so here, so k is an integer, but we write this integer in a binary form. So this is what is an n qubit. And so the observable that we need is the following diagonal operator. So we need an operator that A acting on vector k is equal to k times this state, right? So, okay, so for example, so if n is equal to 3, so this means the following. So that A acting on 0, 0, 0, so this is equal to 0. A acting on 0, 0, 1, so this is equal to 0, 0, 1. A acting on 0, 1, 0. So this is in binary, this is 2. So we get eigenvalue must be equal to 2 for this vector. 0, 1, 0. Then A acting on 0, 1, 1 is equal to 3 times 0, 1, 1, and so on. So this is the observable that we need in quantum computing. So it just takes the basis vector and outputs the same basis vector multiplied by the integer that sits in this basis vector, right? So if we apply this observable to this state, so after measurement, we observe value k with probability norm of ak squared, and the new state is a basis state k, right? So our system will collapse into this basis state. So what this measurement does, it effectively measures the values of all bits of this n qubit. Now, sometimes what we need to do is we need to do only not the full measurement of the value of the qubit, but only partial measurement. So say we only want to observe the value of the first bit. Right? Okay, so as an example, say we take, again, n is equal to 3. And so what do we have here? So the basis is going to be 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. Right? And so suppose we want to measure only not all 3 bits in this qubit, but only the left bit here. So this means that the outcome or the corresponding values that we can observe will be 0 or 1. So this means that for the first 4 basis vectors, the observed value will be 0, and for the last 4 basis vectors, the observed value will be 1. So in this case, so this becomes the observable, right? So now we have an operator on 8-dimensional space that on these 4 basis vectors, it multiplies them by 0 or kills them, right? And for the last 4 basis vectors, it just produces value 1. So as a matrix, so this will be a diagonal matrix with 4 zeros and 4 ones. Right? So this is the observable that corresponds to this partial measurements. So we just trying to observe the value of the first bit. Now, what will happen if our state is just a general state here? So if suppose it's A0 times 0, 0, 0 plus A1 times 0, 0, 1 plus A7 1, 1, 1. Right? So in this case, our space decomposes as a sum of 2 4-dimensional subspaces. So we have a 0 eigenspace. So this is the span of the first 4 basis vectors. And we have 1 eigenspace, which is the span of the last 4 basis vectors. And so what will happen is that any such a vector can be written in 2 parts. So it will be, so the first 4 terms, so will be V0 part, and the last 4 terms will be V1 part. So maybe let's write it more explicitly. So V0 is from A00 up to A3011, and V1 is going to be A4 times 100 plus up to A7 111. Right. And so the outcome of this observation will be probabilistic. So with probability, which is norm of V0 squared, which is A0 squared plus A1 squared plus A2 squared plus A3 squared, we observe value 0, and new state will be V0 divided by norm of V0. So the new state is norm 1. And so with probability, which is the sum from A4 squared up to A7 squared, right? So this is the norm of V1 here. So we observe value 1. So the outcome of our observation will be value 1, and new state will be V1 divided by norm of V1, right? So this is how the partial measurement will work in the settings of n qubits. So for the next example, I wanted to look at the case of an infinite dimensional space of states. And let us look at a particle in a potential well. So we considered this space of states in the previous lecture, right? So here, this space of states V. So these are wave functions. So these are functions on a real interval from 0 to L, and these functions are complex valued. And the Hermitian form on this space is the integral from 0 to L of f of x conjugate times g of x dx. And so usually we also impose some smoothness conditions so that we can write down Schrödinger equation for this function. So as an observable, let's consider the momentum operator. So this operator A is I h d dx. So essentially this is differentiation operator. So this operator taking the derivative. So this means that A applied to f, to the wave function f, it's going to be I h times f prime. Right, so the derivative of this function. Now, what are the eigenvectors for this operator, right? So here we want to solve AF is equal to lambda f, right? So this becomes a differential equation. So we get that I h f prime is equal to lambda f, right? Or f prime is equal to minus lambda I over h times f. And for this, we can easily write down the solution. So here, f of x that satisfies this equation is going to be exp of minus lambda I over h times x, right? So this exponential function is going to be the eigen function for this operator. And so, well, when we consider particles trapped in a potential well, then we also impose the condition that f of 0 and f of L must be equal to 0. So in fact, we see that these eigenfunctions are not going to satisfy these conditions because the norm of this is always equal to 1. So last time we wrote down basic solutions of the Schrödinger equations. And so these functions looked like sine functions. They were sine of lambda kx, where lambda k, we had formulas for lambda k, so they were parameterized by integers. And so this function, well, a sine function, can be written as exponential of lambda ki x minus exponential of minus lambda ki x over 2I. Right? So what we see is that this function is the sum of two eigenfunctions for the momentum operator. And so what we say is that, so with probability 1/2, so we observe momentum that corresponds to lambda. So we can see that the eigenvalue of the momentum operator is h times whatever is in this exponential with I. So this means that so the observed value of the momentum will be h lambda k. And so with probability also 1/2, we observe the value minus h lambda k. So this means that the physical interpretation of this, so that this for this particle trapped in this potential well, right? So with probability 1/2, we will observe this as a right flying particle, and with probability 1/2, we'll observe the same particle as a left flying particle. And in fact, so this particle is going to be a standing wave that will be standing in this potential well. It's instructive to check that this operator is indeed self-adjoint, right? So what do we need to check? So we need to check that f with ag is the same as af with g, right? So what is f with ag? So this is integral from 0 to L, f of x conjugate times I h g prime of x dx, right? And af with g, so this is integral from 0 to L. Then here we will have I h f prime of x, then bar on this, times g of x dx. And so this becomes minus, so because I bar is minus I, integral from 0 to L, h f prime of x, g of x dx. Okay, so how do we see that this and this are the same thing? Well, to see the equality, we can carry out integration by parts. So here, so this, if we integrate by parts, so this is going to be I h f bar times g taken between x equals 0 and x is equal to L, and then minus integral from 0 to L I h f bar prime times g of x dx. But because of this boundary condition, so at the end of the interval, both functions are equal to 0. So this means that this term vanishes, and what we get is this second term is exactly what we have here. So this implies that this I h d dx is self-adjoint. Another natural observation that we can make on this particle is we can try to measure the location of the particle, right? So this is coordinate operator. And this operator B is simply multiplication by x. So this means that BF is equal to x times f. Right? And, well, we can see that this is self-adjoint. So because f with bg, so this is going to be integral from 0 to L f of x bar times x g of x dx, and bf with g, so this is going to be integral from 0 to L x f of x bar times g of x dx. But because x is a real variable, so here x bar is equal to x, and so what we get is that these two things are equal. So here, so this becomes the coordinate operator on the space of these wave functions. And so the eigenfunctions for B are not actual functions, but this is what is called generalized functions. So generalized functions. So also invented by physicists. So these are what's called delta functions. So delta functions. So naively, a delta function is a function that is zero everywhere except for some location A. And in this location A, well, physicists like to think that it has infinite value, right? So really, so what we have is, so a delta function has the property that if we have delta of A of x integrated against some function g of x from 0 to L, then what this produces, it produces the value g of A. So what we have is, so a delta function should be viewed not as a function on interval 0 to 1, but it's a linear functional on the space of these functions. And so because of this, so this is a generalized function. And so this delta function will have the property that x times delta A of x is equal to A times delta A of x. And so what we see is that it's an eigenfunction for the operator B. So the last important point that we need to make when we talk about observables in quantum mechanics is the following question. So when two physical quantities may be observed simultaneously, and the answer to this question is, so we can measure, so we can perform two measurements simultaneously whenever the corresponding observables A and B commute. So this means that A times B is equal to B times A. So the reason for this is purely algebraic. So we can recall that two diagonalizable operators commute if and only if they have a common basis of eigenvectors. So in other words, so if two operators commute and they're diagonalizable, then we can diagonalize them in the same basis. And and if we can diagonalize two operators in the same basis, then they will commute. And this is really important. So if we can diagonalize two observables in the same basis, then it's clear how we can perform measurements at the same time and what will happen, what will be the new collapsed state of the quantum system. So in particular, for n qubit, we can measure the values of all bits simultaneously. Right. Okay, so we discussed the measurement operator for the first bit. So in the same way, we can write down the measurement operator for the second bit. And so these two measurement operators, or these two observables, will commute. And because we have this basis, so if we write the standard basis, right, for n qubit space, so this basis is a basis of eigenvectors for measurements of the first bit, the second bit, and the third bit. So this means that these observables that correspond to measurements of each bit, they will be commuting, right? So because here we see a common basis of eigenvectors for all three observables. And so this tells us that we can measure the values of all bits simultaneously. But if we take the example of a spin of an electron, then we can measure the spin in any direction, right? And so observable for measuring spin along x-axis is given by 1/2 of sigma 1. So this is the Pauli matrix sigma 1, so which is the matrix 0, 1, 1, 0. Right? So for y-axis, so this will be a matrix 1/2 of the second Pauli matrix, so 0i minus I0. So this is, sorry, this minus is here. So this is 1/2 of sigma 2. And so for z-axis, so the corresponding observable is 1/2, and so here it's 1, 0, 0, minus 1. So this is 1/2 of sigma 3. So this sigma 1, sigma 2, and sigma 3, so these are called Pauli matrices. And each of these matrices is self-adjoint, right? So we can see that the real parts are symmetric and the imaginary parts are skew-symmetric. But these matrices do not commute. So sigma j times sigma k is not equal to sigma k times sigma j. And so this means that we cannot, so the conclusion, so we cannot measure spin along x-axis and z-axis simultaneously. Indeed. So what was our physical experiment for measuring spin in z direction? So we have to take and put the electron in a strong magnetic field with which is oriented along z-axis. And we cannot simultaneously put an electron in a magnetic field which goes in z direction and in x direction, right? So because these two magnetic fields will superimpose. And so we can measure the spin along any axis, but only one axis at a time. So this is basically the takeaway from this discussion. And likewise, for our particles in a potential well, so we had two operators of momentum. So A was AH ddx, and B was x. So this is momentum, and this is coordinate. So now let's compute what is A times B applied to F. So this is going to be IH ddx applied to BF. And so this is x, f of x. All right. So now we differentiate, and here we differentiate using product rule. So we get IH f of x plus IH x f prime of x. And if we calculate BA of f, then so this is going to be x times IH f prime of x. And so what we see is that the results are not the same. So AB is not equal to BA. And so the conclusion is that we cannot simultaneously observe coordinate and momentum or velocity of a particle.